Welcome to Purdue University's 2017 Senior Spacecraft Design Presentation. My name is Blair Francis, and I am the Project Manager, and this is Taylor McKenna, the Assistant Project Manager. We are very fortunate to have with us Dr. Buzz Aldrin and Dr. Andrew Aldrin, who advise us as the primary project customers. We are very grateful and excited for the opportunity to share the results of our hard work with you today. We believe that the outcomes presented in this project are relevant to the future of our industry and the future of human space exploration. On September 27, 2016, Elon Musk gave a presentation to the International Astronautical Congress. During this presentation, he made a bold claim, a claim that a colony of 1 million people could be established on the surface of Mars with a time frame of 40 to 100 years. He also pushed that the ticket price could be below $200,000 to make it affordable to anyone who wished to venture there. The objective of Project Destiny is to see whether or not this claim is feasible for the cost and time period provided. In order to actually get 1 million colonists to the surface of Mars, Elon Musk unveiled SpaceX's new architecture, the Interplanetary Transport System, or ITS. The Interplanetary Transport System is able to deliver large amounts of crew and cargo to the surface of Mars cheaper than other comparable launch systems through three fundamental concepts. 1. Full reusability of the upper and lower stage. 2. In-orbit refueling. And 3. Propulsive landing on the surface of Mars.
Elon Musk's presentation failed to include one of the most vital elements of colonizing Mars. How will people live on Mars? In order to conduct a feasibility study, Project Destiny needed to design a Martian colony in order to understand and enumerate the crew and cargo launches necessary to sustain a million-person colony. We assessed the feasibility through three main metrics. 1. Logistics, including manufacturing and launch rates. 2. Cost analysis. And 3. The risk associated with the entire mission. To test the efficiency of the ITS, we had to compare it to newly designed alternatives. Our first option is the SpaceX Direct, which is SpaceX's original design combining cargo and crew in one straight flight to Mars. The second model is the Destiny Direct, designed by Project Destiny to test the efficiency of separating crew and surface cargo, allowing for more passengers aboard the crew model. Finally, we designed the Destiny Taxi, which acts almost as an airliner, transporting colonists to a cycler vehicle to carry people to Mars.
In order to make the Destiny Taxi feasible, the passengers will need more living space on this long trip to Mars. This wouldn't be possible without the use of a cycler vehicle, which provides this living space, which is not provided on the tightly packed launch vehicle. A cycler vehicle works by orbiting the Sun and rendezvousing with both Earth and Mars in a periodic fashion. The cycler trajectory shown rendezvous with Earth and Mars once every 2 1/7 year, or synodic cycle. A synodic cycle is every time Earth and Mars are lined up again to enable launch from Earth to Mars. However, for our actual mission, we have a more complicated cycler trajectory, the S1L1 trajectory. Cyclers using this trajectory will rendezvous with Earth again, then Mars again, every 4 years or 2 synodic cycles. As a result, we will have 2 sets of cycler vehicles to ensure that continuous launches occur between Earth and Mars. The biggest benefit of a cycler vehicle is that this living space can be used on future synodic cycles and does not have to be relaunched every single synodic period. Throughout this project, we will refer to direct flights and taxi cycler flights, so we really want to reiterate the difference between those two architectures. Direct flights begin by launching from the Earth and entering a parking orbit. From this parking orbit, they will receive in-orbit refueling. Once the vehicle is refueled, it'll perform a burn and enter a trajectory that will take it directly towards Mars. Once it approaches Mars, it will actually turn around and do a propulsive landing on the surface. The Taxi Cycler model starts off very similar. It also takes off from Earth and enters a parking orbit, receives in-orbit refueling. However, instead of burning towards Mars, it will perform a burn and enter a hyperbolic rendezvous with the Cycler vehicle we mentioned. Once it rendezvous and docks, the passengers inside the vehicle will enter the Cycler vehicle and live in this until they reach Mars. Once the vehicle actually approaches Mars, they will leave the Cycler, enter the Taxi, separate from the Cycler, and perform a propulsive landing and land on the surface of Mars. No matter which variant you use, all of these vehicles will become refueled and fly on a direct path towards Earth to ensure they can be reused for future flights. The Destiny Taxi and Destiny Direct are not equipped with cargo bays from the Martian surface. As a result, Project Destiny had to develop a new cargo vehicle, or ITS cargo, which can deliver this cargo from Earth to Mars and automatically offload it using a series of cranes. Note that cargo vehicles do not rendezvous with the Cycler and take off and launch on that direct trajectory we mentioned towards Mars. We only have 100 years to deliver 1 million people to the surface of Mars. The ideal arrival rate would actually be to bring a constant amount of people over all 46 cycles, or 100 years. However, this would mean that we would need to bring around 22,000 colonists on the first synodic cycle. As this is logistically infeasible, we actually start at around 300 colonists and steadily increase the arrival rate till we reach our steady arrival rate of 25,000 colonists.
Now, what would the journey of a Martian colonist look like? No matter which variant is chosen, all passengers will leave Earth on an ITS. The only difference is if passengers travel on a Destiny Taxi, in which case they will rendezvous with the Cycler and travel in this vehicle until they get to Mars. One of the benefits of the Cycler is that the Cycler is spun up and colonists experience 1/3 of Earth's gravity on the Cycler. This is the same gravity they will experience on Mars. After they travel on the Cycler, every ITS will land on Mars using the propulsive landing system. We could have landed anywhere as the first travelers on Mars. However, we chose to land on Chryse Planitia, the base of an ancient riverbed also known as Marth Vallis. Now, Chryse Planitia contains two mission-critical resources, basaltic rock and water. The water is found in the form of hydrogen minerals. These hydrogen minerals are similar to what we would call clays on Earth. Our specific colony's location is at one of the closest pairings of these two resources, separated only by 20 kilometers. Once colonists land on Mars, crew and cargo are offloaded from the ITS by a crane system equipped into the ITS. They are then transferred to a transportation vehicle previously launched and ready to meet them once they arrive. This vehicle shown here is designed to carry crew, while the transportation vehicle shown on the bottom is to carry heavy cargo. Colonists will arrive to their temporary shelter, which deployed autonomously prior to their landing. The first 300 colonists will have the same amenities available to them as the final 1 million will have in order to test the efficiency of the technologies. These amenities include individual rooms, recreational facilities, bathrooms, volleyball courts, dining facilities, medical services, a science lab, and a rover port.
One of the primary jobs of the initial 300 colonists is to establish the manufacturing infrastructure for the later colony. One of the most critical resources is water. As stated previously, the water is located about 20 kilometers away in the form of hydrated minerals. At this site, a water extraction plant will be established, and these hydrated minerals will be supplied, where they will be superheated, and the water will be extracted in the form of steam and transported through a steel pipeline. Now obviously a 20-kilometer steel pipeline would be a lot of material to bring from Earth. The way we mitigate this is through the production of steel on Mars, where there's heavy iron abundance. We actually produce this iron through these metal refineries depicted here, which are established by the initial 300 colonists. One of the driving demands for water is actually propellant in the form of methane and oxygen, which is used to refuel the ITS, which ensures their reusability. Methane is produced through the Sabatier reaction of hydrogen and carbon dioxide. The hydrogen is actually extracted from water through hydrogen plants, which break water into its elemental components, hydrogen gas and oxygen gas, through electrolysis. Then the hydrogen is reacted in the Sabatier reactor with carbon dioxide that is extracted naturally from the atmosphere. This fuel is then piped over to ITS landing locations, which have local storage tanks for each of the vehicles. The temporary shelter used by the initial 300 colonists is not a sustainable model for 1 million person colony. As a result, the Martian habitats will be built out of Martian resources. Specifically, basaltic rock will be used to 3D print structures into dug-out quarries on the surface. These structures are printed into these quarries so that they can be buried under 1 meter of regolith. Burying the quarries provides sufficient radiation to bring radiation exposure to safe levels.
We designed our habitats to allow colonists to lead a psychologically and physically healthy lifestyle. However, we are also conducting a feasibility study and therefore need to efficiently house 1 million colonists. In order to integrate these two objectives, we designed a communal living space with shared dining areas, public bathrooms, and central medical facilities, while still providing each colonist with a personal living space. On Mars, colonists will experience a third of Earth's gravity and therefore require more physical activity in order to maintain musculoskeletal health. To accomplish this, we have physical fitness facilities and general purpose athletics courts, while the choice of sport for Martian colonists is volleyball. Physical and psychological health is also dependent on the food production on Mars. Colonists will be sustained by a hydroponic system, which are made out of steel shelves and fiber optic cables. Fiber optics reroute light collected from the sun into the hydroponic shelving, providing the plants with the light necessary to grow efficiently. All colonists will have central access to the amenities described previously through the quarry setup. This configuration will create almost a metropolis feel shared amongst 25,000 colonists.
All of these habitat and manufacturing operations will take power. The power will be provided to our colony through the SAFE 1000 fission reactors. These reactors work by taking the heat of fission reactions and providing it to a generator, which produces electricity. The excess heat will be piped directly into the colony to provide a comfortable living environment. Critical to the psychological health of the colonists is a connection with Earth. Also essential for risk mitigation is continuous contact between the colonists and Earth so that, in an emergency, information can be transmitted to troubleshoot any problems the colony is having. We establish this connection through the Interplanetary Communication System. This system consists of relay satellites that orbit Earth, Mars, and the Sun. The relay stations that orbit Earth and Mars communicate with their respective ground stations using radio frequencies. while the Earth and Mars relay satellites communicate with each other through optical frequencies. This enables high data rates that are going to be necessary for the colony's operation. Normally, Earth and Mars relay satellites can communicate directly, but in the event of a conjunction, or when the Sun passes between Earth and Mars, this Sun-orbiting relay station will redirect the flow of communication. This ensures that there is continuous contact between Earth and Mars at all times throughout the year. The full colony actually just consists of 40 of these 25,000 person quarries. These quarries are sustained by the surrounding nuclear reactors, the water pipeline, and landing fields that provide cargo, people, and any resources necessary to sustain the colony. Note that for the different models, you'll have a different number of landing pads. It can go anywhere from the lower 500s to the upper 800s, depending on which alternative is selected.
Once we designed the colony to sustain 1 million people, Project Destiny needed to take a step back and analyze the feasibility of the mission based on our 3 metrics. First, logistics. Plotted here is a visualization of the average fleet size of each of the 3 variants at any given point of time. To the left of the red line are the ITS launches that are dedicated towards cargo launches. As you can see, SpaceX Direct does not contain any cargo-specific launches, as the cargo is intermixed with the crew. As you can see, there's a clear advantage to taking the ITS taxi, as it can carry more passengers per vehicle. Due to the large fleet sizes, we needed to see if the launch windows had the capacity of supporting these fleet sizes. We determined that SpaceX could handle 6 ITS departing Earth per day. This would include up to 30 launches, as each of the 6 departing ITS could require up to 5 refuelings. With this metric in mind, we could see that SpaceX Direct and the Taxi Cycler fell below the metric, while the Destiny Direct hit the metric. Another factor to consider is SpaceX's ability to build the necessary ITS to meet the launch requirements within the mission timeline. This figure shows the manufacturing rate that SpaceX would need in order to satisfy launch requirements and compensate for vehicle retirements. We estimated that SpaceX could build a maximum of 3 ITS ships per year. Unfortunately, all the variants exceeded this limit, even if we were to disregard the cargo launches. The only vehicle that fell within this limit is the Cycler vehicle. However, this one could be produced by outside sources like Bigelow.
The second component of our feasibility study was to look at cost, specifically to see if the cost could be dropped below $200,000 per colonist. The first step was to look at the total cost of the colony, which was $711 billion, and average it over the million per colonists, which comes out to be about $800,000 per person. We then added this to each of the 3 alternatives we looked at, and we saw that per colonist, it was not possible to get the ticket price below $200,000 without subsidizing this cost in some way, either through private investment or government. We see that the cheapest model was actually the Destiny Direct, coming out at around $2,200,000 per colonist, closely followed by SpaceX's Direct model at $2,300,000, and the Cycler Taxi, which has the most expensive, at $2,600,000. Note that the amount subsidized starts at 86.3% for the Destiny Direct and goes up to around 92.3% for the Cycler Taxi, meaning most of the cost to deliver the colonist and the infrastructure will be subsidized and will not be below $200,000. It is also important to realize that the difference in cost between each of the 3 models isn't that significant, that the Cycler Taxi had only 1% more cost per person than the SpaceX Direct model. The next component was to look at the total cost and average it over the 100 years. We then compared this to a metric we knew, which would be NASA's budget, and specifically the 2016 fiscal budget of $19.3 billion. What we find is that if we look at SpaceX Direct model, It exceeds the 2016 budget by $2.72 billion. The Destiny Direct, which was the cheapest, was at $0.93 billion over the budget, and the Taxi Cycler model was over the budget by 3.79. Due to the scale and number of launches required for this mission, failures will be inevitable and resulting loss of life will be inevitable. What we wanted to determine was the relative failure rates of each model, and we did this by applying the same set of success rates to each of the different models. Specifically, below 100 launches, we used SpaceX's success rate of 93.75% success launches. Up to 1,000, we use the percent of 99.52% success rate, which comes from the Space Shuttle success rate, and anything greater than that will operate at 99.99%. It is critical to note that changing these percentages will change the specific values in terms of the number of failures. However, the same pattern will occur. What we found was that you have more failures as you decrease the capacity of the vehicle. This is because there's a larger number of vehicles required to deliver the same amount of people. As a result, the SpaceX Direct had the highest number of failure rates, the Destiny Direct was closely followed, and the Taxi Cycler with significantly lower number of failure rates due to its much larger capacity. However, when we looked at the number of casualties from these failures, the SpaceX Direct had the lowest number of fatalities, followed by Destiny, and the Taxi Cycler had a significantly larger number of fatalities due to its much larger vehicle capacity. So Elon Musk claimed to put 1 million people on the surface of Mars for under $200,000 within 100 years. Project Destiny found this to be infeasible. We came to this conclusion after evaluating all three alternatives and finding that 1, the manufacturing rate far exceeded SpaceX's capabilities even if we neglected cargo launches. There are simply too many people to be delivered in such a short time period. We found that all three were able to be below the launch rate limit. However, the Destiny Direct was right at this limit, which is why it is in yellow, as it would stress the limits of launch capabilities. All three models were just over NASA's budget. However, it's unrealistic to expect NASA to dedicate not only its entire budget, but some extra in order to pay for this colony. We found that the failure rates decrease as you increase the capacity. However, the risk of losing people increases with this capacity as there's more people on board. If we had to pick one of these three models, we would actually pick the Destiny Taxi. This is because it had the lowest manufacturing requirements, especially if you reduce the number of cargo launches. It had the lowest launch rate per day, and its cost was in margins of the other two launch systems. The risks of losing people could be mitigated through its smaller fleet size, through better inspections, and through the addition of abort systems. So even though we found that establishing a million-person colony in 100 years with the ITS platform is infeasible, the ITS offers excellent capabilities for establishing a colony on Mars. So while SpaceX is headed in the right direction, there's still many improvements that are needed to be made.
We found that NASA's 2016 budget spent for 100 years could almost establish a million-person colony on Mars in the 100-year time frame. Remember in 1961 when sending a human to the moon was completely infeasible? That is, until we did it.
In 2017, landing 1 million people on Mars, well, that's still infeasible, but colonizing Mars is feasible.